Hello, my name is Rafael, and I would like to talk a little bit about the work I did on my PhD thesis at UFMG with Sônia Pinto de Carvalho. So, Dias Caneiro, Alison Comforts, and Pinto de Carvalho asked the question, how do most of the periodic orbits of the plane oval billiard behave? And they answered that saying that generally speaking, plane oval billiards have only a finite number of periodic orbits for a given period. They are all non-degenerative. They also show that the stable and unstable manifolds of two hyperbolic points either do not meet or have at least one transversal homoclinic or heteroclinic point. And any billiard oval with an elliptic diameter can be approximated with a billiard map that has an elliptic island of positive measure. So me and Sonia asked the same question, but for other surfaces. What can you say? And for the hyperbolic plane and the sphere, we can prove the same results. So what are oval billiards on surface? We consider a oval curve a C2 immersion from the circle to the surface that is simple and has positive geodesic curvature. And this will be needed to guarantee that our application is a twist map. And we consider the same problem, like a free movement inside a boundary region. We will move with the geodesic lines inside the billiard map. And we can define a twist map if we consider the angle and the point of collision. So you might ask, why not just do a local perturbation? Like most of these results we can prove using local perturbations. But the problem is that we cannot guarantee that we remain with a billiard map. We expected the opposite, right? We expected that doing a local perturbation we destroy the billiard map. So what we can do is perturb the curve, and we do a normal perturbation, that is, we take a curve and perturb in the direction of the normal unitary vector. This, together with a good expression from the to the derivative of the twist map of the billiard, allow us to do perturbations that change only the curvature. We do some special perturbations and can change only the curvature, remaining the angles of the collisions and the points of the collisions. And this is very good because the derivative depends only on the curvature, the distance, and the angles. So we can control the angles and the distance between the collisions and change the curvature. This will allow us to do some kind of local perturbations. And with this, together with the notion of a Penson arrays is just a curve on your phase space that will give you a geodesic variation. And this will you induce a Jacob field, and using the mirror equation and some other techniques together with these normal perturbations, we can prove that if you have a hyperbolic orbit and they have a tangential intersection, we can break this tangential intersection and make a transversal one. And so the key feature is that it's easier to work with Jacob fields. Each manifold will induce a Jacob field because we will induce a geodesic variation. And with our normal perturbation, they allow us to perturb the derivative in a very specific way. We managed to guarantee transversal intersection of hyperbolic periodic orbits. So we cannot guarantee there will be elliptic orbits, but if they do exist, we ask what is the most common behavior, and we can prove the same results, showing that if you have a two periodic elliptic orbits, which we call a elliptic diameter, we can show that you can perturb this and obtain a billiard that has two periodic elliptic orbits, but with a positive island measure, with positive measure, with an island with positive measure. Sorry. Okay. So how do we create these elliptic islands of positive measure? Boom. We start with a C5 curve. This is because we need to use the Birkhoff normal form and the Moser-Twist theorem. And our normal perturbations, that's all we need. The Birkhoff normal form is a special way to put on your transformation around the elliptic points. So what you do is actually calculate the first Birkhoff coefficient. And together with the Moser-Twist theorem, if the first Birkhoff coefficient is non-zero, the point has elliptic islands with positive measures. So what you do is actually show that we can perturb a billiard and guarantee that the first Birkhoff coefficient is non-zero. And okay, so how are you doing it? How are you doing? So you take your curve, and if it's degenerate, you do a normal perturbation. If it's non-degenerate but is not non-resonance, the resonance is a conditions about the eigenvalues of the elliptic point. We can do a normal perturbation again, because remember, we can control how we perturb normal perturbation. It's not so easy as a local perturbation, but we can do similar things. So we calculate the first Birkhoff coefficient. This is we do some algebraic computations to help us to get a nice expression. And if the first Birkhoff coefficient is zero, we do a normal perturbation that change only the second derivative of the geodesic curvature, because by calculation the first Birkhoff coefficient, we show that this is a function of the distance between the 2 points and the curvature, the first derivative and the second derivative of the curvature, and is linear on the second derivative. So we do a perturbation that that preserves the distance between the collisions, the curvature, the first derivative of the curvatures in each point, but change the second derivative. And if it was zero, then now it's non-zero, and you can guarantee that you have elliptic islands. So this is my short talk about the post. Thank you very much for giving me your time. And any questions, you can send me an email at my email, that is Rafael da Costa Pereira @gmail.com. I'll be glad to answer any of your questions. Again, thank you very much.